All right, it's been one of those Mondays already. I'm a little... I'm on time. Like 30 seconds off. Not too bad. All right, so we have one last thing to cover in Chapter 2, and then we'll get started on Chapter 3. Then at the end of the day, we have a quick quiz to take that shouldn't take very long. So, looking at the last topic in Chapter 2 is atomic mass, and how do we go about determining atomic mass? So since our isotopes, and what is the subatomic particle to make isotopes different from each other? Okay. Since isotopes have different masses for the same element, an atomic mass is a weighted average of an isotope. So this makes the most sense if we just go ahead and do a practice problem and see what we mean by weighted average. So let's say, for example, the periodic table shows magnesium to have a mass of 24.31 AMUs. We also know that magnesium has 3 isotopes. So I have one isotope that's 79, one that's 10. What must be the third one in terms of percentages? 11%. So using weighted averages, we can arrive back at this number. So a weighted average says that you take the mass of this one and you multiply it by its percent. And we'll do that for all 3. So if you don't have your calculator out, just pull that real quick, and we're going to do this one where we already know the answer to it, and then we'll do another one where we don't know the answer. This is just to make sure we all get the same answer. So 24 times 0.79 plus 25 times 0.1 plus 26 times 0.11. And everybody get pretty much 3-1, 3-2, depending on what you... Okay. Did everybody see how we did that? In that case, let's try this one. So let's say if lithium is determined to have 2 isotopes, 92.58% of which have a mass of 7.061 and 7.49 or 7.42%. What is the atomic mass, the average atomic mass? So how do they go about starting this?
Multiply the mass with the 92.58%.
Mm-hmm.
Multiply by 0.9258.
Now, do I do 95.28? Okay. Everybody get at least that far? So, without doing any math, do we expect the mass to be closer to 7 or to 6? Why would it be closer to 7? Right, because 92% of it weighs 7-ish, and very little of it weighs 6-ish. So when you crunch out the numbers, what is your final answer? 6.94. Does that confirm your scientific smartness? Yes, good. That number is closer to 7 than it is to 6. Very good, very good. Questions on using weighted averages? I think there's, oh yeah.
How would you go backwards? Like if it doesn't give you a percentages and you have to apply the percentages?
Okay, so a question would be something like, I know I've done this problem before. Give me a second. I think I have it in my notes. I believe how they want you to do it is that you know that all the percentages add up to 100. It'll take me a minute to find it. Here we go. Here's a good one. So we know the two isotopes, and we know the average atomic mass. So the thing that we're missing is the percentages. But what's the one thing we know about percentages? They have to equal 100. So this turns out to be a little bit of algebra. See if I can get myself another sheet to write on. Because I'll scoot it up. If one of the percentages is x, what does the other one have to be? Or 100 minus x. It can be y, but then I have two unknowns in one equation, and that's not solvable. Now I have, yeah, yucky, that's exactly how it's described. Now I have one equation with just one unknown. So how would I start to solve this algebraic? Okay. So now I have 69.723 equals. So then I take this and I distribute the two parentheses things, right? So I have 70.93 times 100. Actually, I've never done this problem before, so let's see what kind of answer I get. Good so far there? Everybody follow what I did? Okay. So then, what's the next step I need to do? Combine like terms. So I'm going to choose to put all the x's on the right and all the things that are not x on the left. So how do I get this 7,093 over to the left side? Okay. Then what do I do with these two? 68 and the 70. I subtract it, so I do 68 point. Let's see what that turns out to be. Everybody with me? I haven't made any mathematical errors yet? No? Okay, good. So then, what's the next step to get that x by itself? Okay.
So you don't have to worry about sig figs while you're going through this?
I tend not to,
Okay.
and then work it out at the end because it's mostly all the same,
Okay.
because they're all at least 5 digits, and as long as I keep it under 5 at the end. So then what do I need to do to change that to divide by 100, right? Because that's a ridiculous percentage,
Yeah.
right? Or it could be 4, 5, 4, 6. Either one would be fine as long as you show me where you get your sig figs from. So that's x, which is half the question, the percentages of each. What's the second half? Subtract 100. So that is x, but then I also need to know 100 minus x. So if this is x and this is 100 minus x, looking back at how we originally set it up, that 100 minus x is closest to 70 and x is closer to 68. We have a final weight of almost 70. Does the 100 minus x number, is it the heavier percentage? True. Good. I think there's one, is there one of those I'm mastering? Yeah. So if you haven't gotten that far, now you know how to do it. Any other questions on weighted averages? Feel pretty confident? At least not confident. Everyone feel neutral. Neutrally confident.
Yes.
I will take that. I'll take neutrally confident. So at the beginning when I said, yeah, it's been one of those Mondays, I brought down the wrong slides. So, unless you guys want to learn biochemistry, we'll make do with what I have. I have my notes. I just don't have the pictures to go along with them. I just have my little tiny pictures. which are almost illegible. So what we'll do is I will just, if you have the pictures, that'll be great. If not, you will watch me do some amazing drawing today. All right, so we're into chapter 3. Which is molecules, compounds, and chemical equations. Oh, did anybody leave their calculator here on Friday? Because we found one. So if you're missing yours, found one. All right, so big old Roman numeral 1. Going back to our favorite example of hydrogen, oxygen, and water. Does anyone know off the top of their head how hydrogen is normally found as H1 or H2? H2, perfect. What about oxygen? O2. And are they normally found as a solid, liquid, or a gas? Both of them are gases. So everyone familiar with this terminology? When it's in the parentheses with the letter, that means the state of matter it is. So you got your scripty liquid. Those are gases. If it's an S, it'd be a solid. Don't want to assume that everybody's seen that. Right, and so hydrogen is an explosive gas. Oxygen, great for breathing, also for burning. Water is a very different molecule than either hydrogen or oxygen. We've talked about that a lot. And just as a reminder, our compounds that are different than mixtures, a compound elements are combined in fixed, definite proportions. Then we have mixtures. What elements are combined in a variety of proportions. So the question is, how do we know if we have a mixture or a compound, and then how do we go about naming them so that you know what they are? Right, because I could mix up just hydrogen gas and oxygen gas in any kind of combination. Right, I could have 10 parts hydrogen gas and 1 part oxygen gas, or the reverse. But how many hydrogens per 1 oxygen do I have to have if it's water? Right. But water is always 2 hydrogens per 1 oxygen. So does that make hydrogen a compound or a mixture? Compound. It's always the same every time, same ratio. So how do we know what kind of compound we have, and how do we know about naming them? Well, we'll take a look at the chemical bonding going on between them. So chemical bonds. The job of a chemical bond is to hold atoms together in a position. And what participates in the bond? Does anybody know the protons, the neutrons, or the electrons? Perfect. A result of electron interactions. And in here, for at least the first 3/4 of the semester, we're only going to talk about 2 types of bonds. There's a bunch of different bonding choices out there, but we're just going to stick to covalent. And covalent, for the purposes of this class, involves 2 nonmetal elements sharing electrons. Anyone have a guess about what the other main type that may involve metallic elements are? Ionic. And why would metallic ones use ionic bonding? They are more likely to give up or take on an electron. So they are more likely to be ionized. I know defining it with itself is weird, but more ionic bonds involve 2 compounds that are likely to be ionized. I'm going to use the word bonds in quotes. It's not really a bond like a covalent bond. It's more like they are in close proximity to each other. So bonds in quotes. Right, because when we think of covalent bonds, they are going to share an electron. The electron zips between the 2 elements. Or an ionic, quote-unquote, bond, you're actually donating or receiving an electron. So it's not really the same kind of interaction going on there. So let's talk about the ionic bond first. Since metal elements tend to lose or gain electrons, we often see ionic bonds. Forming between a metal and a nonmetal. Typically, the metal is going to be the one that loses an electron. If it loses an electron, does it become positive or negative? It becomes positive. Is it then a cation or an anion? Makes you feel warm and fuzzy because it's positive. So that should be your cation. Even if you're not a cat person, which is hard to believe anybody would not be a cat person. Okay, so then what does that mean about my nonmetal? So if my nonmetal is going to gain an electron, what kind of charge will it take on? Will it become? If it is the negatively charged particle, what is its name? Claudia, that's right. Or Claudia, either one. So then these guys are going to be held together by their opposite charge. So it's not really bonding, it's more that this positive atom element is going to be attracted to this negatively charged one. And this holding together with opposite charges is the ionic bond. That's why I don't call it really a bond. Because there's nothing keeping them there that they could shift around. At this point, I was going to show you a real neat photo from your textbook. This one right here, but it's really tiny. So in your textbook, just go ahead and scoot over to chapter 3 when you get a chance and take a look at, I think it's figure 3.1, 3.2, something like that. So just make a note to look at the picture later because it's good. It's a good picture. You can see it. Okay, so if that's the ionic bond, then we got to take a look at our other choice of bonding. Which is our covalent bond. Bless you. So this is going to be a bond between two nonmetals. That results in the sharing of electrons. So if I have my protons and my neutron hanging out in my nucleus, and I get my electrons zipping around out here. I'll put 4. I have another nonmetal over here. What in actuality is happening is that the electrons, if this was going to make a covalent bond, is that it would be more accurate to represent this where instead of it each of them keep it, it's more they share them. So these ones in the center circles are no longer just the property of one or the other of them, that they are kept in between the two nuclei and are equally distributed in space. How many guys have done Lewis dot diagrams? Quite a few. Okay, so you guys are already thinking bonding because of where the electrons kind of hang out. So this, you realize this is a terrible diagram, but it's not bad for illustrative purposes. What's wrong with my diagram? Anybody know? There's no energy levels. Neither one of them has a full octet, which is also a wah-wah, big lose. So this is a terrible diagram for that reason. But if you don't know what I'm talking about, don't worry. We're getting to that. We're getting to that. About 2 weeks, you guys will totally be on board with my full octet joke. So make a star that you can come back to it, and then when you remember full octet, you're like, oh, that was funny. So leave yourself a little post-it note to come back and laugh at that later. All right, so those are going to be the two types of bonds. So let's talk about chemical formulas and how we know how to name things based on their formula and the type of bonding that they have. All right, chemical formulas. Chemical formulas indicate the elements present. Along with the relative number of each. So the chemical formula tells me which elements are present and then how many of each element are in there. There are three types of ways we could write these formulas. Three types of ways we can write them. The first is an empirical formula. An empirical gives the relative number of each element. We can have a molecular formula. I'll do the definitions and I'll give an example of each. Molecular formula gives the actual number of atoms of each element, or the exact. And then we have a structural formula. Ooh, that's a big cricket crawling across there. So a structural formula gives a diagram of the molecule using sticks and balls or something like that. So, as an example of each type, put on your sheet because I write real big. Our base hydrogen peroxide and water. Let's look at H2O2 first. So the molecular formula gives the exact number of each element, which this is 2 hydrogens for every 2 oxygens. So this is the molecular formula. If the empirical formula gives the relative number of each element, what is the more appropriate empirical formula for hydrogen peroxide?
HO.
Just HO. So you divide them all so that they're in their least common, or they're in their most common, divide by the most common denominator, so it gets to the smallest number possible. Okay, what about water? It's already in its molecular formula. Can I do anything to make it a smaller whole number ratio? So it's also already in its empirical what if I had some made-up compound that looks like that, and I say that that is the molecular formula. That is clearly a fake compound. There's no way that would exist. And I asked for the empirical formula. What would you say the empirical formula is? So the smallest whole number ratio. What if I, one last tricky one, and then we'll do our quiz. What if I said, what if I gave you the empirical formula? Based on just that, could you tell me what the molecular formula is? No. What would you need to maybe figure out what is a piece of information that'd be helpful? If I knew the whole mass of the whole thing, right? If I knew the exact atomic weight of whatever this compound is, then you could go back and you can do some figuring out. But you may be thinking, man, there must be an easier way. There is, and I'll tell you on Wednesday. Cliffhanger. I try to leave a cliffhanger every class. Oh yeah.
What about if there's a number in front of the molecular or
Oh.
empirical formula?
Then it's just talking about how many there are. If it's not written,
So all the elements in the compound?
yes. Yep. So these are all assuming if there's just one. If I say there's two, I'm saying there's two of the whole thing. Yeah, good question. All right, so today is your first individual quiz.